This video is part of CAE Associates Ansys e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an Ansys channel partner since 1985 and have developed our Ansys e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of Ansys courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
I'd like to welcome everybody to the next webinar in a series of webinars provided by CAE Associates. My name is Peter Barrett. The topic of today's webinar is assembly modeling, and we're going to concentrate on different functionalities in Contact, hopefully to improve the solutions you're getting in the problems that you run into. And maybe look at some different techniques maybe that you're not using, or confirm the techniques that you are using and get some feedback from your colleagues as well. So this will be a 30-minute seminar. If you have any questions, you can send those via the chat. There will be a couple polls and a survey at the end. If you want PE credits, please fill out the poll and questionnaire and send in your request for the PE credits. So the question of the day is, how do I effectively manage all of the parts of my assembly, and am I taking advantage of everything I can to get the most efficient solution to contact problems? And contact problems, with most people, myself included, are the most difficult ones to get to converge, and often require a series of different iterations from the user perspective to obtain a solution. And then once you have a solution, you also need to do due diligence to determine if that solution matches the results that you expect to get, and what is the error involved in the assumptions that are going into that solution. So what we're going to go over today is some examples on, first, just kind of managing your contact settings and controlling the automation of generating contact elements and managing the various different contact pairs. Then next we'll get into unconverged solutions, what causes unconverged solutions, and what are some resolutions, and maybe some tools that you haven't used in the past. There's new features that have come out in Ansys each release to address and try to enhance convergence in contact problems. And we'll spend some detail on rigid body motion, since often this is the most common form of contact non-convergence. And then we'll spend a little time looking at evaluating results and looking at interpreting your contact results and how you can make these more accurate. So when you use mechanical to generate your contact elements, most people use the auto detect feature, which will automatically look and find different surfaces within your different bodies and automatically generate contact pairs, contact versus target, on each of these bodies. One of the things to be aware of is, as a user perspective, in using this auto generation, there is a feature where you can adjust the tolerance that Ansys looks at in terms of determining and finding these surfaces that are going to interact. And this can be extremely useful when I have maybe significant interference fits, or I have gaps in parts where I want to make sure that Ansys finds those contact pairs. On the flip side, it can also be used where I may want to tighten the tolerance, where Ansys may be finding contact or thinks it's finding contacts that aren't actually physically in my model. The other thing that I commonly do, the first thing I do when I import an assembly and I have a whole series of different contact surfaces, is use the feature to rename the contact pairs based on their definition. And what that allows you to do is to identify the different interacting surfaces, and it allows you then to group them together as required. Because oftentimes when you spend quite a bit of time in your modeling procedures where maybe you spend time meshing, where you're slicing and dicing to get a nice uniform brick type mesh, the consequence of that is Ansys will generate a lot of contact pairs. And so when it generates all those contact pairs, now it may be advantageous to group them together, specifically for post-processing and also for solution efficiency. Because if you have significant relative sliding between your parts, you want to make sure that those parts aren't sliding from one surface that does have contact to another group of contact, when in reality my body is one continuous set of contact pairs. The other thing that can be very useful in terms of setting up your contact is evaluating your contact groups before you actually run the analysis. You can do that by inserting a contact tool into your connections branch and then generating the initial contact results prior to the solution. And by doing this, now you can evaluate and make sure, validate those contact surfaces that you determined prior to your analysis that you expected them to be in contact. You can also look at the differences of which contact pairs I've defined as bonded versus non-bonded, and what is the geometric gap, and also the corresponding pinball radius. If I want the two parts to see each other in the analysis, I want to make sure that the pinball radius is greater than the gap and also greater than any geometric penetration. And Ansys will provide you in the initial review the status of the contact settings, whether they be bonded in contact, whether they be open or closed, etc. Another thing that can be very useful, a recent enhancement of mechanical for defining and evaluating contact pairs, is the option for multiple body views. So the multiple body view feature allows us to look at the target and contact surfaces independently in a separate body view window. And within that body view window, we can select individual surfaces to either add to or subtract from the defined contact in our particular structure. So we have a series of these different input parameters and associated settings we can do to control our contact groups and pairs and evaluate these. Let me bring up Workbench to show you an example of this. So we have here, I've brought in a part assembly. If I look at my geometry, I have several parts that I've created, a couple bolts, an inner ring. You notice that the inner ring, there's a gap between the inner ring. And so in order to get Ansys to find the contact on that inner ring, I had to go ahead and enhance the slider. So I increased the slider to -100 so it would actually find that contact pair. And then if you look at this assembly, what I've done is provided some slicing and dicing, and that was done to get a nice uniform brick mesh on the structure. But the consequence of that is that Ansys creates individual contact pairs for each of these different groups. And so each of these different groups are individual contact pairs, but I can go in manually and add those together if I want to. And one of the tools often used to add these contact pairs together is you can actually select a series of these. So I could select all the block to bolt to, for instance, highlight these, right-click, and I can simply combine these different contact by merging the selected contact regions. And now they're a single contact region that's specified between these two bodies. If we go into body view format, you notice we can look at the contact surfaces independent of the target surfaces. And maybe you see here there's actually a target surface. Maybe there's one target surface I didn't want to be part of this group, and maybe another surfaces that I did want to be part of this group. Well, I can edit the target surfaces right here in the target view body and simply come over here and change my target surfaces down to just these two surfaces that will interact with my contact body. So it's much easier if I have this multiple view option active to allows me to look at the independently the contact and target surfaces rather than flipping back and forth and rotating my part in the single assembly view. Other things we can look at in terms of the contact tool, we can look at the initial conditions and I'd say generate initial results. So it's going to go through my contact pairs and look and evaluate and determine the initial settings for my different contact pairs. And you notice that it shows me here that I have pairs that are open and pairs that are bonded and pairs that are far open. So I have several different contact regions. Some of these may be erroneous, may want to delete these. Some of these are real. I have in the condition where I have the ring with a gap, I would expect to see an open contact in that particular region. So if we go back to the next topic, which is going to be understanding your unconverged solution. So unconverged solutions in a contact problem can come from force balance not being obtained. They can come from rigid body motion not being obtained, or having rigid body motion not controlled, so my parts are flying through each other. And that's very common with large assemblies. It can be related to material instabilities and element formulation errors that may be an artifact of the material law or maybe just an artifact of the contact analysis itself. So what I like to do now is open up our first poll. So the first poll is to what, for your particular analysis that you run, what are the most common causes of non-convergence that you see in your models? And we'll see what the group as a whole has defined, and I'll share the feedback with everybody so you can get a feel for if you are suffering with lots of problems in rigid body motion or force unbalance, that you'll know that other people are in the same boat. And this is just meant to just kind of get some information, some feedback. It's always challenging to getting these contact problems to run. We're always looking at different ways and features, and hopefully there'll be a couple ideas, maybe things that might be advantageous that maybe you haven't thought of or haven't used for a while, may want to consider using in the future. So I'm going to go ahead and close the poll, and I'll go ahead and share the poll results with everybody. And it looks like for this group that force unbalance is the most common, but second is rigid body motion. And those are by far, in my experience, the two most common forms of non-convergence. So that's kind of consistent with what I would think as well. So if we look at possible solutions for these two types of non-convergence, the first one is the force unbalance. And for force unbalance, generally speaking, the most common approach for resolving force unbalance is to reduce the penalty or normal contact stiffness factor. And since the contact stiffness factor is internally generated based on the material properties in the final mesh, but does not consider the flexibility of your actual physical structure, user intervention is really often necessary to get an efficient converged solution. And if you look at the basic example that you'll see in textbooks in a lot of our training classes, if we have kind of a block-on-block type contact, using a penalty stiffness factor of 1.0, is most efficient, where if we have two flexible bodies, in particular a flexible plate to a solid, a penalty stiffness factor of 0.1. Now, it's important to note that this factor of 0.1 is not actually a 0.1 stiffness, but it's a 0.1 multiplier on the internally calculated stiffness from Ansys. And the Ansys internally calculated stiffness is based on the material properties, so it looks at the modulus elasticity in the underlying elements and the element sizes in the proximity to the contact region. The other feature that often can make a huge difference in contact convergence is not only lowering the contact stiffness, but also telling Ansys to update the stiffness on an iteration by iteration basis. And what this does is allows Ansys to, when a problem is not converging, to reduce the penalty stiffness. If during the iterations it is convergence, it will increase the stiffness. However, this change in stiffness is on the order of 10–20%. It's not going to change it an order of magnitude, which is sometimes required with the overall problem. So it doesn't allow you to not have to go ahead and adjust the normal stiffness factor, but it does allow much more efficient convergence based on when you set a reasonable normal stiffness factor. And the normal stiffness factor useful for is problem dependent, but generally speaking, somewhere between the high end, maybe 10, at the low end, I may use like 0.01 for very flexible bodies. So you're looking like somewhere in that range. The second most common approach to overcome the contact iteration-based non-convergence is iterating on how many actually intermediate solution steps that we force Ansys to run. And the general rule here is the more nonlinearities we have in our problem, the more intermediate sub-steps we should use. If contact is our only nonlinearity, oftentimes using a large number of initial sub-steps and a very small number of minimum sub-steps can be the more efficient pattern to take. If we have other nonlinearities, such as material nonlinearities, forcing a large number of minimum substeps may also be advantageous to accurately capture the stress-strain response of the material law that we've defined. So force unbalance is generally controlled by a combination of these two settings. If rigid body motion is our problem, first we need to identify that. And the way we identify rigid body motion is looking in our output window, and we will see various different warning messages, whether they be degree of freedom limit exceeded, whether they be information about a negative main diagonal, whether they be pivot error messages, or simply by looking at the max to freedom increment and seeing a very large number. So these are the indications of rigid body motion. Sometimes we'll get a converged solution where rigid body motion still exists. In this example here, we have rigid body motion. We have a nice converged solution, but if we look at the displacement of 30,000, obviously rigid body motion has occurred. So how do we eliminate rigid body motion? There are a number of different tools that are commonly used. The best one is usually making a simpler or smaller model to look at. So make a 2D sector, isolate your region, break out different segments of your region, maybe fix all of your components, make them all bonded contact, then slowly release them to standard contact as needed. Adjust your parts. Make sure you don't have existing gaps in your parts when you start your analysis. Sometimes increasing the pinball region, particularly for interference fits, to make sure the two surfaces see each other. And although friction often increases the computational effort, it sometimes can be advantageous in overcoming non-convergence. Something that's been recently introduced to Ansys that we've had some good luck with on some of our problems, particularly for problems with rigid body motion, is a new feature called contact stabilization. Contact stabilization is allowing us to put a damper into our model automatically to prevent rigid body motion. If you look at the example here, we have, with contact stabilization a factor of 0, rigid body motion, the ring flies right out of the socket. If we use a factor of 2, and the contact stabilization factor is similar to the penalty stiffness, where the value you define is a scaled value based on an internally calculated value by Ansys. Now 2 gives me a solution, but it's a very large amount of damping that results in, when I compare running a factor of 0.1 and 0.01 on the peak stress computed in the ring, you see that there's a large error introduced with a large damping factor because I'm sucking energy out of the model that is non-physical. So using the contact stabilization can be an effective tool overcoming non-convergence, but you need to be careful from specifying it and not over-specifying too large a number. You notice from 0.1 to 0.01, there's a negligible difference in the peak stress. So just a little more of what this contact stabilization damping does. It essentially puts in a damper both in the normal direction and the tangential direction. And that damper is a function of pressure over velocity, where the velocity is a pseudo-velocity just relating, because this is generally used for static analysis. So it's allowing Ansys to eliminate this ping-pong type action, or one part running through the other part. And so it's an internal damping. The internal value is computed based on the contact stiffness and the pinball and the radius and the number of steps. And you can control that internally by Ansys. You can also control when Ansys turns on this stabilization. The stabilization is typically turned on for the first load step, although you can activate it for all load steps if you have intermediate solutions. If you run Workbench, Workbench will automatically set the stabilization to 2, meaning to use it at all load steps, and then you input the coefficient, which becomes a real constant related to the contact pair. What makes the most sense for a value? Again, it's problem dependent. I'm seeing for the examples I've run somewhere between 0.1 and 0.01. It also internally will give you a tangential factor that defaults to a percentage, 0.001 of the normal value. So let's take our next poll. So I'm going to open up the next poll, and the question for the next poll is, in previous solutions that you've been able to get convergence, what was the most efficient method that you took in terms of overcoming your non-convergence? You know, was it adjusting the contact stiffness, increasing the number of sub-steps? Sometimes refining the mesh can be an effective tool because we can create more contact elements on the particular interface. And the new feature of course, including contact stabilization is maybe the next time we take this poll in a few months after people have tried this new feature, we may see people adopting that as well. So I'll go ahead and close the poll and share the poll results with everybody. And it's pretty actually interesting, that very uniform, that the solution between refining the mesh, increasing substep, and contact stiffness are all basically, everybody has the same percentages, common ways they go about it. And for many people, I'm sure, the option there was, well, I use all 3 of those methods, and which one do I use all the time? Well, it depends on the particular project and problems. So all of those 3 I concur with are typical solutions for overcoming non-convergence. But hopefully, maybe you'll find in situations with some of your problems in the future that the contact stabilization may be an avenue of overcoming non-convergence that may work for some of your problems. And here's another example of an assembly. This was a 2D axisymmetric problem with a bolt preload. Preload was bolt modeled with an interference fit, and without the contact stabilization, basically all the parts flew apart. With the contact stabilization, we get not uniform converged solution. In terms of defining the contact stabilization, if we look at the original model, we get a nice converged solution with the contact stabilization. It's very simple to define it. As I said, it's in the details pane of your setup. You're simply putting in a stabilization damping factor. Now in this case, for this contact condition with a gap here, the only change I made in terms of the setup was just simply inserting a stabilization damping factor. I used the remaining defaults in terms of normal contact stiffness, etc., and I was able to capture from that the nice contact solution. I can plot contact pressures, I can look at penetration effects, I can look at the different results sets. So go back to our PowerPoint. And so now that I get an analysis, how do I know the accuracy of my model? Well, the first thing you want to do before you do anything is to make sure you check reactions, check your model out, do the common sanity checks. Is that, does my free body diagram make sense? Did my materials define correctly, element types, etc.? When I get to the contact specifically, one of the first things I'm going to look at is contact penetration. Because as we've seen, that we're either adjusting the contact stiffness ourselves or allowing Ansys to adjust the contact stiffness, or a combination of the two. So the contact stiffness plays a major role in the solution procedure. In terms of accuracy, contact penetration is the #1 issue we need to look at. So if we look at contact penetration, if we get a very small value, it indicates that most likely the effects of contact penetration are small. But to truly understand the impact of the penetration, we want to run several different analyses and adjust our input parameters, if possible, and look at and contrast the different solutions. And so here, in this particular example, the contact stiffness was set to 1, which predicted a penetration of 10 to the -6. Contact stiffness was increased to 10, produced a penetration of 10 to the -7. So we got an order of magnitude less penetration. It resulted in a different contact pressure pattern. We had 7,000 psi here. We get a local singular kind of edge effect here. But if we look in the center section here, our values are very similar to that 7,000 value. Most likely the area, or the real area of interest or concern, is the stresses in our individual parts. So if we look at our internal ring and compare the stresses between the contact stiffness factor of 1 and the contact stiffness factor of 10, we notice that the stress does not change, which indicates that from a calculation perspective in terms of error introduced, using a contact stiffness factor of 1 provides a very reasonable result. In terms of display and viewing our contact results, a couple different things that I would recommend. First of all, if I'm going to evaluate contact pressures, I want to use an asymmetric contact pattern so the pressure is actually the true pressure pattern. Because if you're using symmetric contact, the true pressure is an average between the two different solutions that you have. And it's not trivial to get that result out of Ansys. Oftentimes what I'll do is look at the normal stress on the surface as a way of estimating that in that condition. When I display my contact results, averaging, in particular, I should check average versus unaverage for any solution item, but in particular with contact elements, I want to look at the unaveraged solution to get an idea of which elements are in contact and what their status is. And so in the details of any of your plots, under the display option, change this to unaveraged to see the true pattern of which element faces are sliding near contact. In this particular example, those are the two conditions in the local region where the contact occurs. Finally, when we run a solution and get a converged solution, the next time we have to rerun, maybe loads change, materials, we want to change the mesh, that we can make our next solution more efficient by reviewing the results from the existing solution. So the existing solution in this case, if I look at the forced convergence chart, it ran 27 iterations and then bisected, and then ran an additional 3 iterations and then converged for the first substep. So those first 27 solutions were basically thrown away. So they had no real value added in terms of the accuracy of my results. So as an alternative, I would, in this particular condition, is to force additional substeps defined to make sure that I would eliminate this first bisection and go ahead and start with maybe twice as many substeps in my initial setup. And I can look at that. So for instance, if I look at bring back up the model I was looking at here under the analysis settings, under the controls, the initial number of substeps, I can control this value. So maybe if I wanted to increase the initial size, 200 would say start with 1/200th of the load. I have to allow Ansys to do at least that many substeps. And then the minimum number of substeps, really problem dependent, but maybe I'll put 1 or 2 or 5, or if I got a lot of nonlinearity such as plasticity, etc., maybe I'll actually force it to do quite a bit of intermediate substeps. So one of the things we promised to do is keep these webinars to 30 minutes. So this concludes this particular webinar. Welcome any feedback. If anybody has, they can fill out the surveys, send any email information to Christina. I want to thank you for attending, and we look forward to seeing you at our next webinar. Thank you.